Hello everybody, it's your SI Sarah coming at you with some chem tips on how to solve worksheets like this one. 8.2 to 8.7 Lewis structure and covalent bonds. So for the first set of directions, we're going to learn how to write out a Lewis structure where we were writing out the number of electron pairs for each of the compounds given. So as you see in your periodic table, 1A, 2A, 3A, 4A, 5A, 6A, all the way to 8A, there's these little numbers on the top. Those represent the number of electrons for each of these columns. So for this one, 6A, that means that all of these have 6 electrons. And then this one, 4A, all of these have 4 electrons. So that'll be helpful when we're trying to add up the numbers and get the number of pairs. And for a number of pairs, we'll just add them up and then divide by 2. So let's look at the first set. We have this compound C2H6, and so for here we're going to say C equals 4 because we know that it's in 4A column, H equals 1 because it's in the 1A column, and so if there are 2 of them, we'll multiply it by 2, and then if there is 6 of them, multiply by 6, right? So 4 times 2 is 8, 1 times 6 is just 6. We add them all together, we get 14. We divide by 2, and it gives us 17. And then to write them out, we usually pair these together because that means it's just a nice little set of 4. And so if we're having 2, and there's just 6 H's, we can just pair all of these to each set. And that gives us a full pair of electrons. It's completing the octets. Because there's only one here, so when we bond it, it takes out its electrons for hydrogen, and then there's 1, 2, 3, 4 here, and then this is also sharing the bond, so 1, 2, 3, 4. There. So all those are completed. So we know the number of electron pairs are 7, and we can verify that this is right based off of the number of electron pairs, because you got 1, 2, 3, 4, 5, 6, 7. That's how you know you did it right. So let's go to the next one. It's C2H3Cl. We know that C is 4, H is 1, Cl is 7 because it's in 7A column. So when we're adding these up, you get 4 times 2, 8, 1 times 3, 3, because you know 2 and 3, so 2 carbons, 3 hydrogens, and there's only 1 Cl, so that's just 7. 8 plus 3 plus 7 gives us 18, divided by 2 is 9. So that is 9 electron pairs. So when we're writing this out, and I know it's a little smudged here, or compressed, but these should be 2 C's again, a Cl, an H, an H, and an H. And the first thing you do is just check out, before you do a double bond, if these can all fit. So 1, 2, 3, 4, 5. That would lead us without this fixed and without reaching 9. So now we just fill these in, right? And these don't do double bonds. There's only a few exceptions. C, carbon, and oxygen are the few that do have double bonds. So want to keep that in mind. But for Cl, it's just completing 4 sets. And these dots here are called lone pairs because they're not branded in a long line like this. So if we just count all these sets without the double bond, it's just 1, 2, 3, 4, 5, 6, 7, 8, but we're missing one. So if we do this and we get a double bond, then it gets us 9. Okay, so next set. So this is C2H4O. And now we're having a type of group. You know those special types of groups that we learned before in the beginning of the semester? Well, they're back again, and these are really helpful for Lewis structures. So we know that this is C, and this is H, and this is O, And then with this, it's 4, right? Times 2, 1 times 4, 6 times itself, because we know oxygen is in the 6th row. And so if we add them up together, we get 18 divided by 2 is 9. So that's 9 electron pairs. And then when we're doing that, you get C and C, this carbonyl group, which we know is just a C double bonded to an oxygen. An oxygen will still have 2 lone pair sets because it needs to just complete 4. And then 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. If we count all of the bonds, 1, 2, 3, 4, 5, and 6, 7, 8, and 9, we get a full set of 9, which is what we're looking for. Next one. So this guy is C2H3H5NO. So when we're doing that, we get a carbon, a hydrogen, a nitrogen, and an oxygen. Carbon's 4, hydrogen is 1, nitrogen is 5, oxygen is 6, as we know. So then there's 2 of them, 5 of the hydrogens, and 1 of nitrogen and 1 of oxygen. We add them up together, we get 24 divided by 2 is 12. So we would get 12 electron pairs. We set this up like a double bond to C. C and C together. We could set this up as just 3 hydrogens here. But then the amino group, the other 2 hydrogens would be over here. And then the carbonyl group, as we know, has to connect to the carbon. So when we set it up like here, it completes it. We see an amino group is where the H and the H and the N are connected, and the N has a lone pair. The carbonyl group, as we know, carbon, double bond oxygen, 2 lone pairs. We count them up, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that should all equal up to 12. Yeah, so that's 12. So that's how we know we did it right. Okay, so next set of directions is circling the given compound, group in the compound. So in this one, we have an oxamic acid with this setup of a Lewis dot structure. And to circle the amino group, we know is just an H and an H and an N bonded together. It doesn't have to be like this. It doesn't always have to be like that. As long as those look like that and it's a 1 lone pair, you're good. So it'd be that. And then for this one, ethylene glycol, and we're circling the methylene. Methylene is just a C, H, H. And it doesn't have to be like this. This one here shows 2. So you could have it like this or like this. So those are both right. And that's how you would circle those given groups in that compound. And so now for this one, we're trying to look at electronegativity. And we know, given this, that it increases going up and to the right. Order them from high to low. We're given AS, Cl, and P. So if we look here, AS, Cl, and P. So we automatically know Cl is going to have the highest because it's the furthest up and furthest right. Then P, then AS. So it should be Cl, P, AS. Now we're looking at Se, S, and Te. Se, S, Te. If we're going up, it should be S, Se, Te. So from highest to lowest, it should be S, Se, Te. Next, NF and B. So then if we're looking here, N, F, and B. So F is the furthest over, and B is the furthest away. So that means F would have the highest, and B would have the lowest, and N would be in between, so it would be F, N, and B. Now we're looking at the last set, which is talking about polar bonds. So determining if it's polar bond, it's metal to non-metal, and if it's Nonpolar is nonmetal to nonmetal. And the negative atom is just determining the most electronegative, as we determined from the prior set of problems. So for this guy, we're given an H and a chloride, and then a Br and a Br. So for this guy, it's metal, nonmetal. And then to determine that it's polar, metal to nonmetal. So we know, given these options, that the highlighted bond is polar, and then it's the more negative atom would be Cl, as we can see here. And the highlighted bond is not nonpolar, so we know it can't be this one, it can't be that one, because it's not nonpolar. And then for this one, it's nonmetal to nonmetal, so we don't even have to worry about most negative, it's just nonpolar. Okay, so hopefully that makes sense. On to the back page, because there's always more in store. So for this one, we're looking at resonance structures that are Lewis structures that can be written in more than one way. And we can write them for the following structures. So for this, it's SO2. So for S, it's 6, oxygen is 6. And if there's 2 of oxygen, then that's just 12 plus 6, 18, divided by 2 is 9. So we got 9 pairs. So to write out this, we'd have the sulfur in the middle, the oxygens on the side, and let's just do 1, 2 bonds, right? Okay, that's great, but we don't have all the way up to 9. We only have 2 so far. Let's fill up 2 for each. So then 1, 2, 3, 4, 5, 6. Okay, that's still not enough. So then if we give this a double 1, that's 7, still not enough. We can double bond this guy, so then that would almost complete this, but we're missing this set of lone pairs. So that's why we set it up like this, because then you'd get 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs. I would highly recommend doing lone pairs last, and then double bonds second to last. That usually helps when doing these Lewis dot structures. But you can reverse, and the reverse is basically just flipping this guy to the left side. That's what the resonance is. So this would be a full-on resonance. And you have to put the arrow in between to show that it could be this or this. So now for this one, it's CHO2 negative. That means that it's 1 extra electron. So if we're doing this, it's carbon is 4, hydrogen's 1, oxygen is 2. You get 4, 1, 12, and then an extra 1. So that's 18 divided by 2 is 9. You set this up as in that there is a carbon, an oxygen, a hydrogen. Hydrogen you can't add anymore, it's just 1, so it's bonded to 1. Then this one can be bonded and this one could be bonded. But then that's only just 3. We need 9, so we need 6 more. So this guy could do a double bond, one alone pair, I guess. 1 alone pair, 1 alone pair. If that's the case, okay. So that's 1, 2, 3, 4, 5, 6, 7. And then you still need this guy. So if we were to double bond this, that would complete all of oxygen here and all of carbon here. So that would only give us 8. If we just give it another lone pair here, which we can do without having to double bond again, that would give us 9. Now, what they're saying here is that you're just flipping this and this. So the single bond of oxygen is now on top. That's the resonance. And to fix like the ions, to make this appropriately ion, we bracket, square bracket, and then we put its charge at the top right corner. So that would be the resonance for that. And now for this guy here. So to do formal charges, we know it's the valence, and the free one, that's, whatever set of electrons you're found in the periodic table. And then minus the valence of electrons assigned to it. So for this guy, we could just call it 2 dots here, because that's just a single bond. So when we're doing left oxygen, we know that it's automatically going to be 6. And then we just say how many besides 1, because 1's going to be connected to it, how many dots are left. So 1, 2, 3, 4, 5, 6, 7, not 8. So then we just do 6 minus 7, that's a -1 charge, and that's going to be the same for the right one, because it's the same setup. And then for the Cl, it'd be 1, 2, 3, 4, 5, and 6. The lone pairs would always be counted, but the bonded ones will not, because one of the electrons bonded will all count as non-assigned. So then that would just be 7 minus 6, and that gives you a +1. So for left oxygen, it would be a -1, Cl would be a +1, right oxygen would be a -1. Okay. So then this guy, so now we're supposed to draw the Lewis structure for the expanded valence electrons. So this guy is 6, Br is 7, so that would be 6, and then you gotta times this by 6, so it's 42. 6 plus 42 is 48, divided by 2 is 24. But if we're just doing 4, right, the max number of pairs would be 16. So we subtract from 16, we have 8 pairs left over, so we need to make sure we add enough for 8. So if we don't add these two, and we just have this, is just 16. So we add 1, Br. That means that's 1 pair, then we add another Br, 2 pair, then maybe we set this up for double, then that's 3 and 4, 5 and 6, but now we have to finish out the Br, 7 and 8. So if we just add another 2 brackets of the Br and just make sure everything is filled to 3, no double bonds, then you can do that. And why can you make sulfur add extras? Is because if it's beyond a column of 3 or more, you can add more than just 4 bonds. So that's what we'll do here as well for IF5. So I is 7, F is 5, is also 7. That's definitely a 7. And then that is 7. Plus 35 is 42. Divided by 2 is 21. 21 minus 16 is 5 pairs. So this is just 16. But if we add 1, 2, 3, 4, then that would be right. Yeah, because this would be 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. Oh, I forgot. I think you can add like this. And yeah, so that would count there. And yeah, that's how you do that one. And then for bond length, adding on the number of electrons, bonds decreases bond length, but increases energy of the bond. So the more bonds you have, the shorter bond length is going to be, but the higher the bond of energy. So for this one, it's 3. That means the bond length is going to be the shortest, because labeling 3 being the least, 1 being the greatest. So that's shortest. this one's going to be second shortest and that one's going to be the longest. But then you have to consider its opposites. So this means that would be 3, the lowest energy, 2, medium energy, 1, highest energy. And that's how you do all of that. Okay, I hope this helped you. I know we will discuss more in the discussion boards on Canvas. So, that's all.